Okay, so we're now talking about the second, well, this is our second lesson for differential equations, and I just wanted to remind you of some of the vocabulary that we've learned just yesterday in part one of this lesson. I told you that a differential equation is any equation that has a derivative in it. I told you that the highest derivative in the equation, it represents the order. For example, if you see something that has a y double prime, we call that a second order differential equation. But if it only has single derivative, we call that a first order differential equation. Okay, the second thing you need to know is that the solution to a differential equation is a function. So you're actually trying to guess the function that satisfies. So your answers are answers like y equals sine x and y equals c times e to the x, and they're actually functions. Okay. When you first solve a differential equation, you get what's called a general solution, and an initial condition is used to create a particular solution from the general. And you do that just simply by plugging the initial conditions into the general solution. We also talked about how you can graph a differential equation. It looks just like a big field full of slopes. And we also talked about how if you sketch into the slope field the particular solutions, you can see a whole family of curves. Okay, today we're going to talk about how Euler came up with a way to discuss the particular solutions without actually solving the differential equation. Okay, so here's what I'm talking about. Let's say that you were given a specific dy dx. Okay, it equals something. Okay, some crazy derivative, and you don't really recognize what function y is, so you can't quite figure that out. Well, Euler basically said if you knew that, let's use y here, let's say you at least knew that y of 1 is 2 or something, you would at least know something about y, right? You would know that it passes through the point 1, 2. So what he thought was, well, let's just do this. We're going to take the point 1, 2 into consideration, like this. And what we'll do is we'll just create a tangent line, like that. And we can find the slope of that tangent line just by using the differential equation. We don't actually have to solve for y. We're given the slopes. Anything that says dy dx equals is about to give you slopes. So you plug basically the 1 and the 2 into the differential equation, see, and you get the slope. So let's say that the slope turns out to be a half, which is kind of what I drew over here. Then he says, well, one thing's for sure. On a straight line, the slope times the run will give you the rise. So rise is equal to slope times run. That is actually true for a straight line. So he says we can actually use, let's say, a run of delta x, and we can predict the rise in the function. It'll just be the slope times delta x. In other words, dy dx times delta x. And that rise would be called dy, or delta y, I should say. Okay, and then he says, at that point you'll know another point that's at least close to the curve. Okay, so that was his idea. If you really wanted to summarize it as to what the purpose of Euler's method is, you could simply say that Euler's method is used to approximate particular solutions to a differential equation. So particular solutions to a differential equation, which we've been just calling diff EQ. Okay? So what we do is we begin at the point xy that is specified by the initial condition. So they're usually going to give you an initial condition on a differential equation problem. And any problem that asks you to use Euler's method will definitely give you an initial condition. The point will be on the graph of the particular solution. Okay? Now you're going to use basically the differential equation to find the slope dy dx at that point. You're going to increase x then by a small amount delta x. It's usually just given, or sometimes they'll make a statement like a sentence in the instructions, and you can easily figure out what delta x is. And you'll increase the amount delta y by the amount slope times run. So this is Euler's idea. This would then define a brand new point at x plus delta x, because you increase the x by delta x, and comma y plus delta y, because you're increasing the y by delta y. And that lies on the linearization. So it's not right on the curve, but it's close. And then you can use this new point and return to step 2, so you've got this brand new point called x plus delta x, y plus delta y. You then take that, and you'll return back to step 2 and repeat the process. What's going to happen is you're going to be basically constructing a graph of the antiderivative without ever actually anti-differentiating. Okay? Right now I'm only discussing a first order linear differential equation. Okay? A first order differential equation, I should say. So it doesn't have to be linear. Linear means it can have even a y squared in it and everything, but it doesn't have, the ones we're doing are not second order. So there's no two derivatives in there, like no y double primes. Okay, if you happen to want to build a graph that's to the left of the initial point, you have to use a negative value for delta x. Okay, so let's take all the confusion out of this and just do an example. It's really not a very hard thing to learn. And then after we finish explaining this example, or going over this, or even slightly during, I'll show you kind of what's going on so you kind of understand it too. But this particular problem discusses an initial value problem. That just means a differential equation that actually has one extra given, this f of 0 equals 1. They give you a differential equation, they give you an initial condition, f of 0 equals 1, and you're going to use Euler's method in increments of delta x equals 0.2 to approximate f of 1. So here's kind of what's going on, okay? There is this slope field generated by dy dx, okay? And in that slope field lives a family of curves, but only one of them passes through this point, 0, 1. We would like to study that curve without actually solving this differential equation. Okay? All right, so let me show you why, first off, this is a little bit hard to solve. Okay, we're not going to solve this differential equation because I'm thinking of a function where if I take the derivative, that is the same thing as adding on x squared. So just look back at what it says here. Look at the differential equation. This is what it's saying. It's basically saying that if you decide to take the derivative or add x squared, it's the same thing. So I can't even conceive of what function that might be, although I actually do know the answer. Wolfram Alpha is able to give you answers to questions like this, and if you take a diff-EQ class, you'll be able to figure that out too, like actually what function y is. Okay, but we're not going to need to, because Euler's method skirts the issue and it doesn't make us actually study that y curve except by values alone. So let's watch what happens here. This is actually really easy to do. The first thing we realize is that we've been given one point, and that's the point 0, 1. Okay? We can then plug these into the diff-EQ. So basically it's going to be 1 plus 0 squared, which is going to give you 1. Delta x was given in this problem as 0.2. So you don't even have to think about that. It was just given to you. Euler said basically that rise on a straight line is going to be slope of that line times run. That's what this fourth column is saying. So I should be able to just take my slope column, that's the second column, and my run column, that's my third column, and multiply them. So I'm just going to basically do 1 times 0.2, and it gives me 0.2. See? 0.2. All right, now we're going to go ahead and follow over to the fifth column of this table. And the fifth column of the table tells us to add x and delta x. Add x to delta x and y to delta y, see? So let me use the highlighter to show you what's going on here. You're going to be adding this x here, that's the 0, to this delta x here. So in other words, this x to this delta x to create the first coordinate of the new point. Okay, let's do that. All right, so it's going to be like this, 1.2. Where did I get that? I added the 0 in the, I'm sorry, it should be 0.2. I added the 0 and the 0.2, it comes out to 0.2. All right, that's how you do that. Okay. Okay, let's go ahead and do the same thing. This was a 0.2. Now let's go and find y plus delta y. So where are those values? Y plus delta y are this y here and this delta y that you found in the fourth column. See? So you're just going to end up basically with 1.2 for this column. Okay, so I won't highlight every time. I just wanted to kind of show you what I was doing there. And let's go on to the next column. So, or the next row, I should say. The next row starts with 0.2, 1.2. Okay? 0.2, 1.2. And you plug those into the differential equation. So you're basically doing 1.2 plus 0.2 squared, like that, which comes out to be 1.24. Delta x is still 0.2. That's going to remain constant throughout the problem. The third column is still the product of the second and third columns. Or I'm sorry, the fourth column is still the product of the second and third columns. So you're going to multiply 1.24 times 0.2. See? And I'm going to go ahead and erase so I can fit that in here. The answer to that, if you multiply the two columns there, you get 0.248. That. And if you add x to delta x, it's going to go up to 0.4. If you add y to delta y, it's going to go up to 1.448. Like that. Okay? All right, I'd like you to pause the video, and then I'd like you to try to carry on using 0.4, comma 1.448. See if you can finish building this entire table. You actually are not going to need the last row. I have one too many rows typed here. I'm going to pause it and fill it in. So you need to pause it, because if you don't pause it, you're going to see the answers in about 3 seconds. Okay, so I paused it myself and filled in the answers for you in blue. And maybe you didn't use as many digits as I did, but I want to remind you that on the AP exam, you have to have 3 digits of accuracy, so your final answer needs to be that f of 1.0 is approximately 2.763. So you can't have any fewer than 3 digits after the decimal, unless of course it rounds to 2.760 or something, but you really need to have 3 digits there. And I suggest, even if it rounds to 2.760, that you write 2.760, okay? Okay, so what just happened? Like, what have we accomplished with this task? Well, the idea is there was this differential equation, okay? And I imagine it formed some kind of a slope field. I don't know exactly, I don't know. Let's just say it looks something like this, okay? And in this slope field, there are many curves, many curves that would fit. There's ones that fit all through this slope field like that. Okay? But according to the initial condition, we're not interested in all of them. We're only interested in one particular solution, and that is the solution that passes through the point 0, 1. See? So that narrows it down from an infinite family of curves to just this particular blue one right here. See? That's what's going on. Okay, so let's just draw a new quick sketch. We are not just talking about any solution to the diff EQ. We're talking about this particular solution. See? And we'd like to study it, even though we can't really seem to find the equation for it at this stage in our math career. Okay? So what Euler thought we could do is maybe we could just go from 0, since we know this point at least. Maybe we could sort of construct tangent lines and sort of try to follow this curve, even though we don't know its equation. So the first thing he did is he went from 0 to 0.2. And the first slope has a the first one is a slope of 1. Actually, I realize now this is actually quite a bit steeper, so let me show you real quick. This particular solution is actually quite steep. Okay, so the first line we constructed has a slope of 1. It's right here in the table. It's under slope, the slope column, second column. It has a slope of 1 like this, see? And then we found this point, this right end point of this little segment. It's right here. It's 0.2, 1.2. Okay, and then from this point, the 0.2, 1.2, okay, we then constructed another tangent line piggybacking off of that, like this. This one's a little steeper. This one actually has a slope 1.24, see? So I'm exaggerating a bit, but let's just draw it as a little steeper. And we used, basically, the idea is you're using run times slope to get your rise. So you know you want to run by 0.2, so now you're over here at 0.4, and you can calculate how much rise there was by using slope times run. So it turns out now you're at the second point in the table. See? And you just keep doing this, and then eventually you get out here to 0.6 and 0.8, and finally 1.0. And you find yourself, now I'm going to zoom out again. Here is the particular curve. That's not quite right there. Sorry, let me erase that. Meant to pass through 0, 1, not the origin. Okay, so here is the particular solution. Here is our efforts to model it with straight lines. We basically have found this red endpoint on the far right. We'll call it point P. Our goal was actually to find this point up here, the blue one, which was 1 comma f of 1. But since we can't solve for f of 1, we did the best we could, and we followed this little red guy. And we ended up at point P, which isn't too far off. I suppose it would get further from the blue if we kept going. If we tried to find like f of 2, you could see that the gap right here would be quite large. Okay, but we've only gone out one space, and we did it in 5 increments. So we would use point P in place of the blue point. All right, so this is Euler's way of approximating f of 1, and he used this idea of rise being slope times run. It's actually quite ingenious. Now, what is one way we could make this more accurate? Well, you would want to make a smaller delta x. The smaller your delta x, the closer the red curve will be to the blue curve. Okay, another thing that we understand is that because the blue curve is clearly concave up, at these points in this particular region of our graph, we can clearly see that the p value is underneath the blue curve. So we've seen this kind of thing before. The concave up nature of the blue curve causes us to under-approximate the blue point. So the red point is below the blue, and that's because of the concavity of our blue curve. All right, now what would happen if we wanted to study points to the left of the initial point given? Well, you'd have to use a negative delta x to work to from right to left. So that's what our next example is about. So let me clear my ink and let's move on to the next page. So you can flip your page over there. Let's go on to the next page here. Okay. All right, now, this one's different for a couple reasons. One is the differential equation is actually a little bit simpler. There's no x squared in it. I still don't necessarily need to solve this. I want to study the particular solutions without actually solving the equation. This time there's a slight difference in the way things are worded. They said that y is 3 when x is 2, but that's just another way of saying that f of 2 is 3. Or that 2, 3 is on the particular solution. In fact, this is our starting point in the table, see? Okay? This time they didn't really tell us delta x, but it says use Euler's method with 5 equal steps to approximate y when x is 1.5. So basically we're trying to go from 2.0 down to 1.5. We're going from x equals 2 to x equals 1.5 using 5 stages, And this is obviously a decrease. So I think what we're going to need to do is use a negative 0.1. That'll take us from 2.0 to 1.9, from 1.9 down to 1.8, from 1.8 down to 1.7, and from 1.7 down to 1.6, and lastly from 1.6 to 1.5. Okay? All right, so once you've kind of determined your delta x, you can simply fill in that row of the table. So this is not going to change for the problems we do. Looks like that. All right, the rest is what we were doing a minute ago. If you want to pause the video and try it, you can. I'm just going to go ahead and do the first row, and then I'm going to pause it and populate the whole table, and then I'll unpause it so you can see what I did. Okay, so the first thing you do is you plug these into the differential equation, and you get basically 4 minus 3, which is 1. Multiply the slope column times the run column, and that gives you the rise column. See? So that's going to give you negative 0.1. Then you're going to add your x to your delta x, your y to your delta y, and you're going to get 1.9 comma 2.9 for this particular one, which becomes the next entry, the first entry on the next row. Okay, now I'm going to go ahead and fill in the rest of the table in red, and when I unpause it, you will see the answers. Actually, I think I'll use blue. Go ahead and check your answers with mine. Okay. I might want to pause it again and check them over. But it looks to me like our answers right over here, I'm underlining it in red, it's 2.61. Well, you can either truncate or round, either 2.610, or if you round it to the nearest thousandth, 2.611. So I'm going to go ahead and just truncate it, 2.610. The graders will take either truncation or rounding. Okay? All right. So you can see that the slopes were actually decreasing on this one. See that? As you go to the left. So all that means is you went from x equals 2 backwards to x equals 1.5, and the slopes got less steep. So I believe this is, again, another example where the curve was concave up, as you can see from a little sketch there, and that we have an under approximation. Okay, because we were basically taking this point first and then building tangent lines backwards. So we're underneath our curve again. And this basically is probably pretty accurate. We're using 0.1s this time. The curve is not as bendy as the last one, maybe. Although I wouldn't bet my life on it. I'm just thinking this is a little bit better approximation than the last problem. The truth is, the only way to really know how well you did and how accurate 2.610 is if you actually knew what f at 1.5 was, right? And the only way we know that is if you learned how to actually find the antiderivative of the diff EQ, at which point you would then know y, in other words f, and you could plug in 1.5. Okay, but that's a 6.4 topic, which we'll take care of that then. So we will actually take a handful of diff EQs and learn to solve them. All right. So this is a BC concept that's very important. It's Euler's method. The purpose, to use the idea of slope times run equals rise, and several iterations of that to approximate a particular solution without actually solving a differential equation. Good job, Euler.